Ho ho ho! Can you hear the bells? All right, so welcome to part 2 of this algorithmic modeling challenge where we were trying to break down how to create Koch stars, this fractal shape, or Koch snowflakes, I think they're also called. In the previous video, I showed how the algorithm works and what are the steps that we were going to follow in order to create this algorithm, and I implemented it using vanilla Grasshopper, which is a visual programming language for Rhino, which is a 3D modeling environment. What I'm going to do in this video is I'm going to apply the same logic, but I'm going to implement it by using C# scripting within the Grasshopper environment. It's going to look something like this. It's just going to be basically a recursive algorithm that takes the polyline and applies the process of Koch subdivision over and over again, so that we can just choose how many levels of subdivisions we want to do, and the algorithm will just start subdividing this geometry. Okay, so very simple. It's like sort of like Christmas inspired, because Christmas is coming very soon at the time of this recording. So let's take a look at how this would work. Okay, let's get hands-on. A quick refresher, if you are not coming from the previous video where I did this in vanilla Grasshopper, I just want to remind you that the way that we're going to do this is we have a polyline, and then that polyline is basically a sequence of points. So any triangle can be thought of 4 points, 0, 1, 2, and 3, which is the same point as the beginning, so that the polyline closes up. And then what we're going to do is we're going to subdivide each one of those segments into 3 segments and find the 2 points in the middle at 1/3 and 2/3. We're also going to find another point at the center, and we're going to move it perpendicular to the segment so that we can find that third point that makes the pin of the triangle off the curve, right? And we're going to move it a distance that is going to be equal to the side of the smaller triangle we're subdividing times square root of 3 divided by 2, which is the height of an equilateral triangle. And once we have that, we can then do a little bit of like smart order manipulation and put all the points in the right order, so that when we join them with a polyline, we get this element here. We get like the full subdivision polyline. Another reminder is that the way we're going to find these perpendicular vectors is by using the cross product of a vector that joins the 2 points of the segment we're working with a vector that is perpendicular to the plane where the polyline lies. And remember that the cross product of 2 vectors is a perpendicular vector, so that's why this is going to be the way we're going to find those perpendicular vectors. I have explained all this thing in a bit more detail in the previous video, so if you have questions or if this process is not clear, please go back to the previous video where I explained this process a little better. Okay, so what we're going to do now is we're going to implement all this logic, the idea of taking a polyline as pairs of points, and for each pair of point, generate an algorithm that finds the intermediate points, at 1/3, the one that is perpendicularly moved and the one at 2/3, and then put them together in a list in order to generate a polyline. We're going to do that manually, and we're going to do that by writing recursive algorithms. Okay, so let's take a look at how we can implement that. Right, so we are here. I just created a triangle in Rhino, and then I'm going to I just brought that triangle into Grasshopper by creating an empty curve component and setting it to this triangle. And then I have created this C# script component here where I have renamed the first input to polyline, and I'm going to right click here and make sure that the type of that input is going to be, it's overflowing on my other screen, that the type of the input is going to be polyline here, and then the second is going to be levels, which is going to be an integer, because I want to know how many levels of recursion and subdivision I want to do. So I'm going to plug those two here, and then at this point I think I'm ready to start writing some code here. And the first thing that I'm going to do, and I'm going to rename the output, I'm going to rename it Koch, for example. So now that I'm here, the first thing that I would like to do is, I think you know me already, and you know that I like that I like being very functional about how I write my algorithm, so that then I can copy paste code around my different programs. So the way I'm going to do this is I am going to first we're going to implement the idea of taking a polyline, so the full triangle, and then subdividing each one of the sides of that triangle and creating one iteration of the Koch subdivision. So I'm going to focus first on taking the full polyline and creating a second polyline that has all the subdivision. And then once we have that working as a function, I will create another function that will be like a superset of that, in a way, which is going to take any polyline and start applying this process over and then again many levels of depth. So I'm going to subdivide this process in those two different ways. So the first thing that I would like to do then is I'm going to create a function that is going to take a polyline and is going to apply that subdivision and is going to return another polyline with the Koch subdivision. Okay, so I'm going to call that Koch subdivision, for example. This algorithm is going to take a polyline as an input, so pol, for example, and it's going to return another polyline object. Okay, so I take a polyline, I subdivide it, and I return that polyline. And then, to make sure that this works, what I'm going to do is, just for the sake of development, while I'm developing this algorithm, I'm just simply going to take whatever polyline is given to me and subdivide it with this algorithm. So I'm just going to subdivide it once. And then this, so that it works right now, I'm just going to return the simple algorithm first. And you can see that this is working, and that I have no errors here. And if I plug a geometry output here, I do get the simple polyline that I still haven't modified whatsoever. Okay, so this is working right now, more or less. So now here, I need to write an algorithm that takes this polyline and subdivides that polyline. All right. So first, one thing that I probably want to do is I want to make sure that I know how many points are in my polyline. Okay, because yeah, I'm working with a triangle, but maybe the user is giving me a polyline that is not a triangle, that is a quad, or is that a more complex thing. So my algorithm will depend on how many points there are in my polyline. So I'm going to say I'm going to create a variable called point count, which is going to be equal to pol dot and the count property of polylines. This is very specific to Rhino Common. Okay. And then what I would like to do is I'm going to start a new empty polyline. And to this new empty polyline, the one that I will eventually be returning, I'm going to start adding strategically all these points that I'm going to be generating. So I'm going to create another polyline. I'm going to call this sub, and this is going to be a new empty polyline with nothing on it. All right, new empty polyline. And just for starters, what I'm going to do is, because I'm going to write an algorithm that is going to look at each one of these segments, the first segment, the second segment, and the third segment, I'm going to kickstart this algorithm by adding the first point, this one here, by adding it so that every time I look at a segment, what I do is I generate these 3 points here. And then when I look at the next segment, I generate these 3 points here. And when I look at the next segment, I generate these 3 points here. Therefore, there is no redundancy. There is no overlapping. There is no duality. So there are no points that overlap with each other, except for the last one, which has to overlap so that this polyline is closed. But this makes the algorithm a little cleaner. So what I'm going to do then is I'm going to say, well, to the polyline that I just created that is empty, I'm going to add the first point, and the first point is going to be, oh, sorry, my keyboard does strange things this day. To this polyline, I'm going to add From the polyline, I'm going to add the first point of that polyline, which I can find with the first property of polylines inside of Rhino. If I do that, and if I now, instead of returning the original polyline, I return this subdividing one, then what I get is that I have nothing because I have a polyline with only 1 point. So it gives me an error, which is okay. All right, this is fine. All right, so what I want to do now is I want to write an algorithm that goes over each one of the pairs of points, so 0 and 1, 1 and 2, and 2 and 3, for each one of the segments of my polyline. So what I'm going to do is I'm going to create a for loop. So, and if I have 4 points, I'm going to iterate 3 times because I have 3 segments. So what I'm going to do is I'm going to create a for loop, and I'm going to start that for loop with the value of 1, so that, because I've already looked at point 0 on my, can you see my cursor here? Because I've already looked at point 0 here. Now I'm going to start looking at point 1, point 2, and point 3 as the meaningful points for each one of the segments that I'm going to be working with. So I'm going to go back and say I'm going to start with point 1. I is going to have to be less than how many points are in my polyline, and I'm going to increase by 1 unit on every for loop. So here I'm going to iterate over each segment of the polyline. For each segment of the polyline, first I'm going to cherry pick the starting point and the end point of those segments. And remember, if I go back here and I say, well, I'm going to start with point 1 as the representative for this segment here. So therefore, the starting point of this segment is going to be the index, so 1 minus 1, so it's going to be 0. And then the endpoint is going to be this one here. So the way I can do that is I can say, I'm going to move this out of my head, and I'm going to say point 3D, the starting point is going to be equal to the points in the polyline, I minus 1. Let me explain what I've done. The polyline class in Rhino Common allows you to use the square bracket notation as if it was a list or if it was an array to retrieve the points that are part of this polyline. Because again, and you've heard me say this like 1,000 times, polylines are just simply lists of points. So it makes sense that you can use the list access notation, so square brackets, for example, to just cherry pick those points. So the start point is going to be whatever point we have at position I minus 1. And the end point is going to be the point that we actually have at position Y. So that's why if we do 1, 2, 3, we have 0, 1, 1, 2, and 2, 3. Alrighty. Okay, so the next thing that I would like to do is I would like to add to this polyline. So for each segment, the first thing that I'm going to do is I'm going to add this point here. The point that is at 1/3 of the length of that segment. How are we going to do that? Well, I'm going to use some code that I wrote for a previous geometry gem in which we found a point between 2 points that was at a relative distance. Okay, so that was actually in geometry gem number 7. And if you're interested in learning how that works, just feel free to go to this link to the geometry gem number 7 and figure that out. But basically, we wrote a function that given 2 points and a relative length from 0 to 1 between those 2 points, it gave us the point that was at that length. So what that means is that I can create a new point here, and I'm going to call that point 1/3, for example. And that point 1/3 is going to be a point that is going to be at a relative length between my start and my end point that is going to be at 1/3 of that length. So I could type here 0.3333, or I could type here 1 divided by 3.0. And I want to highlight how I'm doing 3.0 to make sure that this division is not an integer division, but it's a division with decimal part. All right. So I have that, and now that I have this, I can add that point at 1/3 to my polyline. And if I run this code, I should start already getting stuff. All right, which is cool. So I have a polyline that goes where? So it goes from my first point, the one that I added manually, to the 1/3, the one at the 1/3, and the one at the 1/3. Okay, so something is already working here. All right, so I'm going to get here get endpoints of this segment, and then compute first third point. Now, the next thing that I would like to do is I would like to find this point here. I would like to find the point that is offset from the axis by a particular distance. Okay, this is going to be the one that is going to be a bit more complicated, but it's not going to be that difficult anyway. So what we're going to do is, if you remember from the previous video, what we did is we calculated the vector that was the axis of this segment. We unitized it, and then we did a vector multiplication. Sorry, we did a cross product with a vector that was perpendicular to the plane of this polyline. And because we were doing the cross product, because the cross product gave us the vector that was perpendicular to these two. So that vector that I'm trying to find here. Okay, so that you can go to the previous video to see a bit more visual way of how this happened. So we're going to compute the point at the tip of the subdivision. So what we're going to do first is we're going to calculate the axis vector. So vector 3D axis is going to be equal to a vector that goes from the starting point of the segment to the end point of the segment. So that is in Rhino common, that's very easy to do. You can just subtract the end point from the starting point and you get that vector. Now, the second vector that we're going to use is we're going to find a perpendicular vector. All right, the vector that is perpendicular to this polyline. Right now, for the sake of getting an early version of this working, I'm just going to hard code that the perpendicular vector needs to be the z-axis. All right, but we will play a little bit with that later on. So I'm just going to hard code the fact that that vector has to be the z-axis, the world z-axis. All right, therefore, as I do that, actually, let me call this normal, for example. As I do that, then the perpendicular vector to this line is going to be the cross product of these two vectors. So I can do that in Rhino common by saying vector cross product, and then the first vector is going to be the axis, and the second vector is going to be the normal. All right. However, I have forgotten one thing, which is that the axis needs to be normalized, because I want all the vectors that I'm working, I want them to be unit length, so that when I scale them up or down, I can control their length perfectly. So I forgot to say that axis, I want to unitize this vector. And because this vector is now unit, and this vector by definition from Rhino common is also unit, I know that the perpendicular vector is also going to be an unit vector. All right? All right. So now what I need to do is I need to take this perpendicular vector, all right, this one that I created here, that right now is unit length, and I need to scale that up in a way that makes sense with the size of this triangle. So what I need to do is I need to find the length of this small triangle and multiply it by the square root of 3 divided by 2. How am I going to do that? Well, first of all, I need to find the length of this segment. All right, and this is something that we already did also in a previous geometry gem. In geometry gem number 2, we wrote an algorithm that calculates the distance between 2 points. And this is very simple Pythagorean algorithm. If you want to learn how this works, you're welcome to check that geometry gem. So what we're going to do here is, first of all, we're going to calculate A is going to be equal to the distance between the starting point and the end point. All right. Then we're going to calculate a third of that. So that's going to be A divided by 3.0. And then we're going to calculate height. So the hypothetical height of this triangle, which is going to be A3 times square root of 3 divided by 2. So this is going to be equal to A3 times math dot square root of the value of 3 divided by 2.0. All right. Okay, so I think we are ready to scale up this perpendicular vector by this amount. So the way we can do that is by saying that this perpendicular vector should be scaled up by a factor of h. And because perpendicular is unit, we know that now the result of this operation will be a vector with the exact length of h. If your system that you're working with, we can do this increment with a scalar on a vector class in Rhino Common because it has this operator overrides. But if you don't have that possibility, maybe you have something like, do we have scale? No. Do we have length computes? This only computes the length. So I don't know, maybe your system has a way of scaling vectors. I'm not sure, but this could also be, for us, it could also be the same as saying vector perp is going to be equal to itself multiplied by this height. All right. Okay, so we are good. Now the next thing that we need to do is we need to find this point here at the middle, and given this point, and we need to move that point by the perpendicular vector that we just generated. So that is going to be very simple given all the code that we already have. So I'm going to create vector 3D. The point in the middle is going to be a point that is going to be point along the line relative, like we just did before. And then it's going to be start, it's going to be end, and it's going to be a point at a distance 0.5. All right. And as if I have this, then what I can do is now I can say to that point I want to add the perpendicular vector. So whatever that point was before, move it by that perpendicular vector that I just calculated. And at that point, the point is already at this location that we just generated. So this point is already here. So I can now go ahead and say to my subdivisions, I want to add this middle point that I just created. And let's see if this works. No, we have an error. What is going on here? So we cannot convert from point 3D to in line 92. Okay, so, so sorry. So this should be a point 3D object. All right, yes. So my bad. Okay, so it looks like this is somehow working. We have a polyline that starts here, goes to the first third, goes to the tip, and then jumps here, then goes here, and then jumps here, and goes here. So let me, how do I get the points of a polyline? No, there was a function. Let me, hold on. Yes, so I want to take this polyline and I want to see the control points of the polyline, which is basically the vertices, because I want to make sure that I am getting all, yes. So you see 1, 2, 3, 1, 2, 1, 2. So we're already there. We're getting very close. Okay. Wonderful. The next thing that I need to do is to my algorithm, I need to add the point that is here, the point that is here, and the point that is here. The point that is at 2/3 of the length of each one of the segments. So that's going to be super easy given what we've done already. So we're going to compute the second third point. And that's going to be, I'm just going to copy paste this and I'm going to say 0.23 is going to be a point relative from start to end at 2/3. And then I'm going to add 0.23 to that. If I run this, you can see that now this point is already showing up, all right? And then finally add the endpoint. So sub.add the endpoint so that we get this point into the mix, this point into the mix, and this one so that the polyline closes properly. As I do that, boom, we got this. Yoo-hoo-hoo! So let's recap a little bit what we've done. We have created this function that takes a polyline, all right? And given any polyline, it performs Koch subdivision and returns another polyline that has this, that is based on the original one, but it has all this subdivision with these triangles, all right? So this in itself is already a very neat function that can work on any polyline, all right? But now the trick is we want to write something that makes this function call itself over and over again recursively on the same polyline so that we can start creating more and more subdivisions. All right, let's take a look at how would we do that. The way we're going to do this is going to be very similar to what we did before, and it's going to be fairly easy actually. Just like we created a function to perform the one subdivision, what I would like to do now is I would like to create a function that I'm going to call the Koch star or the Koch Snowflake or whatever, that is going to take as an input, it's going to take a polyline, right? And it's going to take the amount of levels that we want to subdivide that polyline in, and it's going to return another polyline where the Koch subdivision, the recursive Koch subdivision, has been applied to. All right, so the input is going to be a polyline and the return is also going to be another polyline. Now, what we can do is basically very similar to what we did in vanilla Grasshopper. What you basically see is that we did really apply the same algorithm, the same subdivision to the output of one component. We applied it, we used it as the input for the next iteration of the subdivision. And the output of that subdivision, we used it for as the input of the next subdivision. So here, we're going to use a very similar procedure where the first thing that I'm going to do is I'm going to create a new polyline that I'm going to call the star. And that star is going to start, that star is going to start, yes, it's going to start as a copy of the polyline that is going to be given to me, like the baseline, the triangle, all right? And then what I need to do is I need to write a for loop where this many times we're going to take the start and we're going to subdivide it with Koch subdivision. How does that work? I'm going to just write a simple for loop, but I'm saying I'm going to start at 0, I is going to be less than levels so that we only iterate those many times, all right? And then I'm going to write something here. And now that I'm remembering, I'm just going to crank this down to 2 because you will see that 10 is actually a lot of levels. So I'm going to just crank that down. And then here, what I'm going to say is for each one of my levels of subdivision, what I want to do is I want to perform Koch subdivision to the polyline that I already have. So I want to perform Koch subdivision over the star polyline. All right. But what am I going to do now? Well, this function is going to return a polyline that has been applied this subdivision. The interesting thing is that what I can do is I can say, well, the result of that, I want to actually make it star, because what I want to do is I want to say over and over, the result of the first subdivision is what I want the star to become, so that on the next iteration, that is what gets subdivided again as a second level, and the result of that is the star that I want to pass on to the third iteration of the for loop, gets subdivided, etc., etc. So basically, I'm taking what I had before, I'm subdividing it, and I'm using it as the input that gets sent to the next iteration of the for loop, and therefore it gets subdivided again. The way to do that is by taking the result of that and overriding the previous result that I had, so that the star starts becoming more and more complex over and over. And then finally, the result of that is what I'm going to return with this with this function. So you can see, like, I just finished this. Wait, and let's. Is this going to work? Wait. Like 3 levels. No, it's not working. Oh no, that was a. Oh yes, sorry. That was lame. Because I didn't change the code on the main component, which is still using simple Koch subdivision. So what I want to do is I want to change this to the full Koch star subdivision and then pass in here levels. And as I click start, whoa, we got 2 subdivisions, 3 subdivisions, 4 subdivisions. Let me turn this off here. 5 subdivisions, 6 subdivisions, and let me crank this all the way up to 10. At which point my computer, you see, it took half a second to compute, and it's actually not rendering, but that's only because the density of the geometry is so much that it only starts rendering when I zoom in. And you can see how my computer is getting laggy, but you can also see how I'm zooming in and zooming in, and it looks like there's like infinite of this thing. You know, I can still keep zooming in, zooming in. You know how much subdivision have we done here? Woohoo! You know, and then we're getting to the 10th level. All right. How awesome is this? It's like fractal geometry. Let me crank this down a little bit because 5 is too much. And you see now. Alrighty. Okay, so let me recap. What we have just written is basically a very simple function that takes the starting polyline and performs Koch subdivision over it this many times and overwrites the previous result. And that's why we are generating over and over more and more subdivision over the same original polyline. Okay? All right. So as I showed in my previous example, you can see that this can be applied to a triangle, and I'm just going to fill this in with a boundary surface, which is going to be a super expensive operation because of all this detail, and my computer is actually frozen right now. Whoa! Yes, you see, this took 12 seconds to compute. Not cool. All right, I'm going to remove that, and then, but you can apply that to any polyline, because there's nothing really in our algorithm that tells us that the input has to be a perfect triangle. Nothing like that, because we have worked at the level of each one of the single segments. We can apply this to any polyline. And also, as I described before, it doesn't really have to be a planar polyline. This I can apply it to a spatial polyline, and then you can see that the subdivision is just because I've been using a perpendicular C. The subdivision is just trying to stay as horizontal as possible, respecting the slope of the curve. All right. Now, there are things that I could do to modify this. So for example, here we hard-coded the fact that the normal vector is the z-axis. So we could pass in that as an input, for example. So let's say I wanted to hard-code here. What is the normal? What is the normal that I'm going to be using for these calculations? And this is going to be a vector 3D. Okay? And then I'm going to pass here a z vector, which is with unit -1. All right. And then what I'm going to do this is I'm going to introduce this normal into the algorithms. So here I'm going to accept that this should have another input that is called the normal. All right. And then I'm going to accept that, make that this has to be another input that is going to be the normal. And this is the normal that I will be using here instead of the hard-coded z-axis. So I'm going to accept that. And then here I'm also going to pass in the normal value. And here I'm going to pass in the normal value. And whoop. And if I do that, you're going to see that now the Koch curve is going to flip and it's going to become inverted, and it's going to be an anti-snowflake or something like that. That's what I read in Wikipedia. But you see, now it's inverted and it goes inwards. I kind of like it better here. All right. And I think this can use a boundary. Oh, well, I'm just going to crack this down a little bit. Yes, so we can do a surface. Oh, I cannot do a boundary surface here. Planar surface routine. Ah, because it's not planar. All right. So yeah, it has to be planar to give me a. All right. But I think this is pretty cool. This could be a really nice cutout for a laser cut, huh? Yeah. Alrighty. So I'm going to go back to a normal. I'm going to go back to a normal Koch star, and I'm going to do 7 subdivisions here. Which, oh no, the surface component. Oh my god, this is gonna take forever to render. Okay, so I think I just broke my computer. So with this, I think I'm going to close up the video. This was Kochstar, Christmas, whatever, snowflakes, fractal geometry. I hope you like this video, and if you like the work that we do here at Parametric Camp, please feel free to subscribe, to like these videos, to tell your friends. My name is Jose Luis. If you're watching this right before Christmas, I want to wish you a happy holiday. If you're watching this in the future, I also want to wish you a happy holiday anyway, because why not? All right. Thanks a lot. And if you're interested in more of this, I'm about to record a new geometry, a new algorithmic modeling, which is going to be a Sierpinski tree, which is another form of fractal geometry. Okay, so you should be getting some links somewhere here, up or down or somewhere. But in the meantime, thanks a lot for being here. And you can see that this still hasn't, it still hasn't finished calculating. It's still frozen. All right. So yeah, so no 7 subdivisions. Be careful with the boundary surface component. It's very heavy apparently. Thanks a lot and have a good one.